Wednesday.
That's right. U of I Professor Paul Kwiat shows us how the sun works and the quantum process of tunneling in a demo that you can even eat at the very end.
Hey everyone, nice to see you. Hope you're all doing well. Today we have a big day ahead of us. We're going to try and explain how the sun works. Where does the energy from the sun come from? And what does that have to do with this demo that we showed last time? Okay, I'm sure you maybe know that the energy from the sun comes from the process of nuclear fusion. And what that means is that I have to get two protons to be able to join together. And in the sun, there's actually a fairly complicated process where I actually have 4 protons that eventually have to come to become a helium nucleus. So I've got these 4 protons, and eventually I have to stick them together to become 2 protons and 2 neutrons. Don't worry about the fact that somehow it seems like 2 charges are missing. That's not really relevant for what we need. The big question, though, is how does that give us energy? We need to know where the energy from the sun comes from. And this is related to this famous equation I'm sure you've probably heard, E equals mc squared. So in this case, the E is the energy that we have, the equivalent energy, and m is the mass, and c is the speed of light. Oh, in this case, it turns out that the 4 individual protons that I start out with are a little bit heavier than when they're all joined together to form the helium nucleus. So not much, less than 1%, but that extra energy that you have when they is released when they bind together to become this helium nucleus. And that's basically where all the energy of the sun comes from. Okay, but it turns out there's another mystery. And the mystery is, well, how do we actually get 2 protons to stick together? So they're only going to stick together if they're basically on top of each other, but they're both positively charged. And I'm sure you've heard that like charges repel. And so as I try to push them together, they're going to repel each other. And in fact, the force of repulsion goes like 1 over the distance squared between them. And because they're very small, protons are only like 10 to the minus 15 meters in radius. That's a very small number. When I square that, that's an extremely small number. And then I take 1 over that to get the force. So that means that as I'm trying to push them together, it takes an enormous amount of force to get them to stick together. And even though the sun is very hot and they're flying at each other, none of them basically have enough energy to smash into each other. They come close, but they never actually do that. So it turns out the solution, how they're able to do that, is that they behave quantum mechanically. And there's this phenomenon in quantum mechanics called tunneling that's really kind of interesting. So let me just show my cherry tomato in a bowl here. And I'm just going to let it go on one side. And the original potential energy, the fact that it's raised up, becomes kinetic energy, and then it climbs up again. But it's never going to leave the bowl if I'm just letting it go, right? It never has enough energy to climb up over the other side of the rim. But quantum mechanically, it's possible for the particle to basically disappear on one side and then reappear on the other side and then come flying away. So this is what would be happening with the protons. So let me just show a quick animation of that. So this is supposed to be a particle coming against a wall that normally it couldn't go through. It would just always bounce off. It doesn't have enough energy to go over the wall. And we see that what happens is that a little bit of there's a small chance that a particle leaks through. This is called quantum tunneling. And in fact, we've seen this before. If I come back to us. So I showed this demo with a glass of water before, and let me just quickly remind us what that was. So I said that if I press my thumb very hard on the side of this, you can, so nominally there's no light, I can't see, all the light is reflecting off the outside of the glass, but if I press my thumb really close, I'm able to see that. Okay, so we talked about that last time, and let me just go back one more time to my slides and make the connection with this tunneling. We said before I had this total internal reflection where all the light is bouncing off the surface of the glass, and I'm not able to see. But if I can bring my fingerprint close enough, then I have frustrated total internal reflection, and then I'm able to see the fact that my fingertip is there. So the way we should understand this now, according to quantum mechanics, is that the light is made of particles that we call photons. They don't want to be in this outer space here outside the glass, so they all totally reflect. But if I can bring my fingertip close enough, then some of those photons will tunnel across the gap into the ridges on my fingertip, and that's how I'm able to see that. So I encourage you to do this trick again at home. You can see it for yourself and understand that that is the same basic process that's going on in the sun that's able to get our protons close enough that they can fuse and give us the energy. And the best part about this demo is you can eat it at the end. Okay, hope to see you guys later. Bye-bye.